Okay, my name is Masatoshi Kajita from NICT in Tokyo, Japan. I want to give a presentation with the title Precision Frequency Measurement of Molecules. The physical laws are established based on measurements, but always there are some certain uncertainties. And by reducing the measurement uncertainty, a new discrepancy with the previous laws can be discovered, and development of new physics is required. The precision measurements have been performed particularly with atomic transition frequencies, and for several transitions, uncertainty of 10 to minus 18th have been obtained. But in this talk, I want to discuss the possibility of precision measurement of molecular transition frequencies. Time and frequency is a physical value which we can measure with the lowest measurement uncertainty. And I want to say that it is fundamental of precision measurement of all physical values. For example, telling about mass of elemental particles are estimated from precision measurement of atomic transition frequencies. Particularly electron mass is so. And about length, wavelength of light with accurate frequency can be accurate length scale. And atomic clock was developed after the World War II. But atomic clock is clocks based on the atomic transition frequencies. At first, it was developed in the microwave transition area. And the measurement uncertainty was reduced drastically by the development of atomic clock. Now, the standard of time and frequency is defined by the cesium transition frequencies in microwave region. This transition is measured with the uncertainties of 10 to minus 13th with the commercial type atomic clock using thermal beams. But with the laboratory type using cold atoms, the uncertainty is reduced to 5 times 10 to minus 16th. In principle, optical transition frequencies is more advantageous for precision measurement because finer scale of time. But at first, optical frequency was not measured with counter like microwaves. But there was a revolution at the beginning of this century. Optical frequency comb was made it possible to measure the frequency of laser light. So the measurement of optical transition frequencies became one of the hottest topics for physicists. And measurements of uncertainty of 10 to minus 13th, 10 to minus 18th was obtained for these transition frequencies. The uncertainty of 10 to minus 18th means error of 1 second. Yeah, it takes period since the birth of the universe. And I want to introduce a few contribution of precision measurement of physics. At first, we can show the detection of relativistic effects. As you know, for special relativity, time goes slower in a moving frame. And theory of general relativity with gravitational potential field, time goes slower. These effects were detected using atomic clocks, although it could not be observed using crystal clocks. And another example is atomic clock is useful to search the variation in fundamental constants. There is a question if fundamental constants are really constant. With a slight difference of fundamental constants, the size of the universe is quite different. For example, if the electromagnetic field is stronger, there would be no heavy atoms because of the stronger repulsion force between protons. If the electromagnetic field is weaker, there would be no molecular bonding. Anyway, we can exist only with the proper fundamental constants. So it might be difficult to understand the coincidence. The fundamental constant may be changing by time of space. And we can consider we live in a time and space with the proper value of constants. So when there is a variation of fundamental constant, there is a variation in transition frequency like this. And there we can determine the sensitive parameter lambda like this. But this sensitivity parameter has dependence on the transitions. So the variation of fundamental constant is monitored from the variation in the ratio between two different transition frequencies like this. So, but the variation in the frequency ratio may be larger than the, must be larger than the measurement uncertainty. So the detector variation in fundamental constant is limited by the measurement uncertainty. The most recent estimation of variation in fundamental fine structure constant is very small, order of 10 to the minus 18th per year. So there are also some other examples, but precision measurement of atomic transition frequencies gave much contribution of physics. But there are also some phenomena which we cannot observe just from atomic transition frequencies, but can be observed with molecular transition frequencies. So precision measurement of molecular transition frequencies are also very useful. The first example is that search for the variation in proton-electron mass ratio by precision measurement of molecular vibrational or rotation transition frequencies, because vibration transition frequencies is inverse proportional to the square root of proton-electron mass ratio, and rotation transition frequency is inverse proportional to the proton-electron mass ratio. But the atomic optical transition frequencies, the sensitivity is 5 orders smaller. Another example of a merit of precision measurement of molecular transition frequency is such a violation of symmetry of vibrational transition frequencies of optical isomers of chiral molecules. If we can observe the violation of symmetry, by some difference in vibration transition frequencies between optical isomers, we can explain that the abundance of optical isomers are not always equal. So I want to discuss what determines measurement uncertainty. There are two kinds of uncertainties. One is statistic uncertainty. It is because all transition spectrum has certain spectrum width, spectrum line width, and the measurement results distribute randomly within the spectrum line width. So just averaging, we can determine the real value, and the statistic uncertainty is reduced increasing measurement samples. So I don't discuss with this uncertainty in detail. More important is systematic uncertainty, because the transition frequency shifted by the electric field we call Stark shift, and electric field gradient we call electric quadrupole shift, and magnetic field we call Zeeman shift. And there is some shift caused by relativistic effect, the quadratic Doppler shift or gravitational redshift. So there is a question why precision measurement of molecular transition frequencies are more difficult than atomic transition frequencies. One reason is that molecules have vibrational rotational states. So it is difficult to localize in a selected vibration-rotational and also hyperfine state. To overcome this difficulty, I propose to use diatomic molecules, and it is preferable at least one atom has 0 nuclear spin. Then the energy structure is relatively simple, and optical pumping to a selected state is possible using broadband lasers. And for molecular ions, we can prepare in a state selective preparation by photoionization. Another difficulty is it is difficult to reduce kinetic energy to below 1 millikelvin by laser cooling. It is required for precision measurement because the trap area must be smaller than the wavelength of probe laser. It is easy for microwave, but for optical measurement, it is required. And it is required to suppress quadratic Doppler shift by laser cooling. But recently, laser cooling of several molecules was succeeded. Yeah, I talk it later about calcium fluoride or strontium fluoride. And molecular ions can be sympathetic cooled with co-trapped laser-cooled ion. So there is a question, which molecular transition is useful for precision measurement? I must argue that the vibrational transition with without any change of angular momentum quantum numbers, because molecular shape depends on the angular momentum quantum numbers. Angular momentum determines the direction distribution of wave function. But changing the vibrational state, the figure does not change, just change the slight change of bonding length. For example, the molecules are spherical symmetric with the lowest rotational state. Then the Stark, Zeeman, or elliptic quadrupole shifts and upper and lower states are almost equal, and the inference to the transition frequencies are very, very small, almost two orders smaller than the each energy states energy shift. So which vibrational transition should be measured? Yeah, we can select transition which is convenient to prepare to probe lasers. But I must say, particularly for near infrared region, the line width narrower than 10 millihertz has been attained using cold silicon cavity. Then ultra narrow line width laser is very useful to observe the transition spectrum of molecular transitions with narrow natural line width, particularly with homonuclear molecules. And it is useful for vibrational transition of homonuclear diatomic molecular ion. So at first, I want to tell about molecular ion in a linear trap. In a linear trapping system, molecular ion is co-trapped with atomic ion, and atomic ion is laser cooled. Then the kinetic energy is reduced, and string crystal is formed on the trap axis where the electric field is 0. So I want to argue the merit to use homonuclear diatomic molecular ions. For homonuclear molecular ion, there is no electric dipole coupling between different vibrational rotational states in the electric ground state. So there is no perturbation by black body radiation in infrared region. For heteronuclear molecules, there is dipole coupling between different vibration-rotational states. So unhopeful transition can be induced by infrared blackbody radiation. And another merit is that Stark shift is 5 orders smaller than heteronuclear molecular ions, because it is coupling is only with electric excited states. So I want to discuss the rotational state of homonuclear diatomic molecular ions. Molecular ions is produced by photoionization in a selective vibration rotational state. And it is preferable to use state without nuclear spin 0. Total nuclear spin is 0. At first, I want to consider with nitrogen molecular ion. So with this state, electron spin is 1/2. Electron angular momentum is 0. I want to argue that 15N2 plus isotope is useful to prepare rotational state N is 0 and the nuclear spin is 0 with a simple structure. Because for 15N2 plus, even rotational state is automatically 0 nuclear spin. For odd rotational state, nuclear spin is 1. With conventional 14N2 plus molecular ion, nuclear spin can be 0 or 2 with even rotational state. And it is not easy to select 0 nuclear spin molecular ion. I consider also O2 molecular ion because 16O nuclear spin is 0. It is a merit, but there is another complication. Electron spin is 1/2, and electron angular momentum on axis is 1. This omega is the total electron angular momentum, the sum of spin and orbital angular momentum is 1/2 or 3/2. So with this excited electron state, rotational state N is not defined. Only total angular momentum is defined. So for 15N2 plus, I want to propose this vibrational transition frequency, but rotational state is 0 to 0. This is important thing. With this state transition, Zeeman shift and electric quadrupole shifts are 0. And DC Stark shift is very small, and also blackbody radiation shift is very small. It is much smaller than the previous atomic clocks. But this transition is, one photon electric transition is forbidden. So I considered 2 methods. One is Raman transition using 2 lasers. By considering 2 photon transitions, yeah, the light shift can be large, but light shift can be eliminated by proper combination if or when one laser gives positive shift and the other laser gives negative shift, and total shift can be eliminated. Another method is 2 photon absorption. With this transition, we can obtain very narrow line width. Then with this light shift, with the order of 10⁻⁵, if we use the laser light with 10 MHz line width. But this light shift can be eliminated by hyper-Ramsey or auto-Ramsey. It is difficult to explain this method, rather complicated technology, but it became possible to suppress light shifts. Recently, 1 photon magnetic transition was found to be possible by a group in Basel. Anyway, systematic and statistic uncertainty can be lower than 10⁻⁸. And also for O2 plus molecular ion, for J is 1/2 to 1/2. Then electric quadrupole shift is 0. Zeeman shift exists, but it is strictly linear with the coefficient of 10⁻⁵ per Gauss. It is much smaller than previous atomic clocks, and it is perfectly eliminated, averaging 2 by 2 M is 1/2 to 1/2 or -1/2 to -1/2. And this historic shift and blackbody radiation shifts are small. And also this transition is 1 photon forbidden. And this, for this molecular transition, the light shift is always negative. So I considered also only 2 photon absorption with which we can obtain ultra-narrow line width. Also, with this molecular ion, systematic and statistic uncertainty can be lower than 10 to the -18th. So there is a question, how can we monitor the transition? For single atomic ions, we can monitor observing fluorescence from cyclotransition. Cyclotransition is the cycle of laser-induced excitation and de-excitation with spontaneous emission. But for molecular ion, it is difficult because spontaneous emission transition is possible to different states. So the cycle does not possible. So there is a technology called quantumological method was developed. It is a little complicated to explain, but it is a technology to inform the information of molecular ion to that of atomic ion. If molecular ion is state 1, atomic ion is alpha. If molecular ion is state 2, atomic ion is beta. So another proposal is to use neutral molecules in optical lattice. Cold molecules can be trapped by standing wave laser light. The lambdic region means the area smaller than the wavelength of probe laser. So the first order Doppler effect is not existed. And we can measure with many molecules. And trap laser frequency trap laser gives some energy shift. And it can give the shift in the transition frequency, but it depends on the trap laser frequency. And with the frequency, which we call magic frequency, the energy shift at upper and lower states are equal, and the Stark shift, the light shift becomes 0. And to suppress the collision shift, it is required to use 3-dimensional lattice. But the magic frequency should be independent to the polarization. In this station, laser cooling succeeded with calcium fluoride molecules in Harvard University or Imperial College. And for calcium fluoride transition is applicable with 3-dimensional lattice because the light shift is independent of polarization. For example, with this transition, and rotational state to 0 to 0 state, the uncertainty of 10 to the 17th can be obtained, seeing the Zeeman shift, DC Stark shift, and blackbody radiation shift. And I could estimate also magic frequencies for the measurement of vibrational state 0 to 1 transition. And transition can be monitored by Raman transition using 2 lasers, different signs of shift. In conclusion, the precision measurement of molecular transition frequencies is useful to develop new physics observing phenomena which cannot be observed just by atomic transition frequencies. And the pure vibrational transition frequencies of 15N2 plus or 16O2 plus vibrational transition frequency can be measured with the precision of 10 to the 18th. And also the calcium fluoride molecule are laser cooled and trapped in the optical lattice. So the N is 0 to 0 vibration transition frequency can be measured with the precision of 10 to the 17th. Finally, I hear the project in UK, there is a network called QSNet, comparing different kinds of atomic clocks. And two of them are nitrogen molecular ion, and another one is calcium fluoride molecular ion, which are in procedure to develop.